Hello everybody again, Joaquim again. We already did introductions. So first of all, this is a joint work with two people, Mario Souto, a student friend of mine, and Álvaro, his advisor. And Mario was going to come, however, he has a little job in Amazon right now, so he couldn't come for this week. However, he's at Amazon teaching everybody how to use JuMP, so he's doing his part. Okay, so the idea here is to present this SDP solver that we have been working on. So, okay, we have heard a lot about what is an SDP, and this is some reasonably generic formulation for an SDP, the primal and the dual. So you have like a linear objective function, a bunch of linear constraints, and a semi-definite constraint. So for the rest of this talk, I will keep one semi-definite constraint. So all my variables belong to this same big thing, and I can discuss more about that later, whether we want to extend that or not. Just to be a little bit more flexible, since we all like to use inequalities, moreover, instead of only equalities, we have rewritten the formulation to this form so that we have equalities and inequalities, which is easier to model rather than, okay, add a slack variable here, which will just make the semi-definite cron grow too much. So why does SDP matters? SDP is a big enough class of problems that encompasses second-order cones, linear programming, quadratic programming, and a little bit. If you want to do like something like logdats, you want to use semi-definite cones in some part of that. There are other parts of convex optimization that are not included in semi-definite programming. Ulf's talk went over most of these too. Okay, so there's also many problems of interest that lie in the SDP family. And a second use is that for the guys from mixed integer programming is that it's very good for relaxations. If you solve some semi-definite relaxation, it might give you good bounds for your mixed integer program. So some classical applications of SDP, some control problems, robust structural design, eigenvalue optimization, optimal power flow, machine learning, and the relaxations I've been talking about. One big problem of SDP is that sometimes the size of the problem grows too fast. So that's sort of one of the reasons we split the inequality constraints, because okay, if you want to add just one extra slack variable, your matrix will have to grow by one side. So, but instead of adding one variable, you're adding like two n variables. Some other problem is sparsity. So linear solvers are very, very good at handling sparsity patterns. However, SDP solvers had big problems for a while, but recently there are these core-DAO decomposition methods that are making everything much easier. And the second difficulty was formulating an SDP would be very hard in the past. Sometimes you had to do a lot of things by hands, and that's one of the problems we are solving with JuMP. Other alternatives are CVXPy and convex for a while. And the fourth big problem is that handling really large SDP problems is very hard for some classical interior point method SDP solvers. And in this talk, we are going to take a lot of advantage of this claim. So an SDP with M constraints admits a solution with a rank much smaller than the M constraints. And actually, in practice, many problems do have even less rank. So if you have some radio network for optimal power flow, the rank of your solution will be 1. Very frequently, the ranks are very small if they doesn't even reach 1. There are many relaxations where when they are tight, the ranks are 1, and so this is a big thing. And something that makes some people crazy while using these SDP relaxations is that although the SDP might have a very low rank solution, many interior point methods usually compute a full rank solution because it would just land in some optimal solution that is not the one with lowest rank. Although you can prove that exists, sometimes you cannot reach that using interior point methods. And it's very common that you don't reach that. And there have been a lot of work exploiting these low rank structures, for example, in matrix factorization. But one weird thing about matrix factorization is that you take a convex problem, you split that into a matrix factorization that most of the time is solved by non-convex methods. So it's a little bit weird, but it works in many cases. So our goals. The goal of this talk is to present what we did, which is a first-order method for solving SDPs, which is based on a technique called primal-dual hybrid gradient, which is very common from the guys from imaging. We want to provide optimal primal solutions, and as a result, we will be able to provide some dual solutions, not all the duals. It's a first-order method, and all the primals will be available, although some of the duals will not, but it's already something good. As I said in the beginning, it admits inequalities without having to add slack variables, which would grow too much in the complexity. And the main thing is we will exploit low rank structure in this framework to make it not only faster, but you actually have high probability of reaching low rank solutions. And so we're making a open source solver, which we'll call for now ProxSDP. So a little bit about the algorithm. I will go very fast on that. There should be a paper released soon, but not now. So the whole algorithm will be based on something that is it's called a proximal point algorithm. More specifically, like I said before, a primal-dual hybrid gradient descent following this paper of Chambol and Pock. And it's easy to show. It's reasonably easy to show. It's in the paper, which is not available yet, that the convergence rate is optimal for this kind of algorithm. And so basically you cannot do better than that for a first order algorithm. What?
What is that?
I think it's the size of the variables. In some sort encoding plus constraints. I'm not sure now. I have to review that. Maybe I will see Nesterov's paper. So I will just show the algorithm just to point a few things in it. It looks like an ADMM algorithm. So what I want to show is that the algorithm only has 3 basic steps. So the first step over there is updating a X matrix. That's a matrix which is a semi-definite matrix. And everything that is going on there is inside the parentheses, there are matrix multiplications and a sum of matrices. And the proj means a projection on the semi-definite cone. It means that you make the spectral decomposition of the matrix and you just take the positive eigenvalues, and that truncation is the projection we are looking for. So, and the other steps are, the second step only involves matrix multiplications and sums. And the third step is just a projection. So if y divided by alpha is bigger than b, it's different than b, it will be set to b. If it's larger than h for the inequalities, it will be set to h. So it's just a truncation in some sense. So all the algorithm does is some spectral decomposition, matrix multiplication, and truncations. So very simple. In practice, you could do that. Actually, the first version was done in Python. It's really easy to do. But then you want to add some performance to that. We decided to move that to Julia, and it got interesting results. But let me go forward because I haven't spoke anything about the low rank structure so far. So a little bit about the low rank structure. As I showed you the algorithm, you can see that the hardest part is the spectral decomposition, which is O to the n of 3 in the side of the matrix. This one I know. So if you want to reduce that, you could use some prior knowledge. So, okay, if it grows too much, it will be too hard to solve that problem because n to the cube might be too hard for a single step of the iteration. So if you know the largest rank possible for your problem, you could go for it. Okay, I know that is R, and you can do some incomplete spectral decomposition, which only gets the first R eigenvalues of the matrix, and then you truncate the rest. But then you usually don't know that. So what we're going to do in the algorithm is to change that number adaptively. So as I was saying before, the truncated decomposition, you just grab the highest R eigenvalues and take its eigenvectors, sum those, and you get your approximation for the matrix. And there is this old theorem that says that the difference between the real projection and the truncated projection is not bigger than basically n minus r times the largest eigenvalue you have. Okay. And combining that, we're combining this approximation to this approximated fixed point iteration, which is in this paper by Eckstein and Bert-Sikas, which they present some convergence criterion for that. It basically just says that in relatively mild conditions, you can converge just using the approximated fixed point instead of having to do full steps of the composition all the time. So the algorithm is changed to this. We have a new loop, which is just a loop for changing the size of the approximated spectral decomposition. So you basically start with, say, 1, and then you solve the problem. If you don't converge, then you increase the rank of the matrix, and you do so on and so forth. Okay, so we implemented that algorithm in Julia using a lot of the Julia linear algebra good stuff. And we wanted to put that below JuMP. It's already working with MOI. To work with JuMP, it's like 2 hours of work. I just have to fix some functions. And this solver has very good performance on low rank structure and provides primal solutions and some of the dual solutions. So a few case studies just to take an idea about that. There's this interesting problem called multiple input, multiple output problem. So you have multiple transmitters, you have a channel, and then you have multiple receivers. So what happens here is that you are transmitting a discrete signal of -1s and 1s, you can say, and then you receive a signal on the other side. However, the signal on the other side has passed to the channel and has some random noise. Okay, so this problem can be reformulated. Actually, solving the problem, once you have the y, finding the axis. Once you actually h is a prior also. You know h and you know y. Solving for x is just you can solve that with a quadratic, just basically linear regression. And then least squares. And then you can convert that problem to this very simple SDP problem, which is saying, okay, you have some linear objective, you want the diagonal of a matrix to be 1, you want this matrix to be positive definite, this constraint is redundant, and you want all the entries of the matrix to be built between -1 and 1. And if you have this constraint, then your formulation is exact, but it's non-convex. However, if the signal to noise ratio is really large, you can relax that constraint and just solve the problem, and it will give you some good approximation about the signal. And then we solve this problem with 3 solvers. We used CSDP, SCS, and low rank primal-dual SDP, which is the ProxSDP solver. So N is the number of variables, M the number of constraints, P I think is just the product of both of them, and then you have the times to solve the problem. So this problem can get really big if you have you have too many variables and constraints over here. And so CSDP doesn't even solve medium-sized instances. It stalls and it stays there forever, and it says, oh, I can solve that. SCS can do a little better for that. However, the thing is, SCS is doing first order instead of second order. So in some sense, it was designed to be better than CSDP for this kind of problems. And of course, ProxSDP is also a first order method, is designed to be better at this problem. But you can see that there's a lot of room for improvement. We could beat SCS by far in this problem. Just not to stay with one more problem. There is this graph equipartition problem from SDP-lib. So we solved again with SCS, CSDP, but now I just added an extra column where I'm solving for ProxDef without the low rank structure. I'm always doing full matrix decomposition. And the last one is the problem with approximate spectral decomposition. So as you can see, the problem typically has low rank, although the side of the matrix is n. The side of the matrix is n, so 124, 250, to 500, up to 1,000. And the rank is much smaller than the full rank of a matrix. So what happens is that ProxDef works very well for this problem. CSDP, actually it should be black over here. CSDP is very good for this problem. Maybe for some reason it was already in SDP-lib, so somebody tweaked it so that CSDP works well on that problem, because it performs well on most SDP-lib problems. I think it's comparing where it's compared to SDPA, some solvers like that. Please?
Sorry, have you compiled with SDP-3?
What?
SDP-3?
No, I haven't. It's very hard to use SDP-3. You have it's the MATLAB one. You have to. I think I don't even have MATLAB anymore. These other are open source, so I have them in my machine, and Benoit made an interface for them for JuMP and MOI. So it's really easy to compare. That's the main reason they're there. I should also compare to Mosaic, which has an interface right now.
So SCS also does a full
I'm not sure. It does?
Yeah.
Okay.
So why is there a gap when you run both algorithms to do the full eigenvalue?
Okay. First of all, I would say there is a gap, but they scale pretty similarly. There is a maybe a constant difference between them, but I'm not sure the reason why. Maybe SCS is too generic, and so being able to handle the other cones might make the pure SDP solving interface not so good. I would be curious to know why, if SCS could do better or
Did you
not.
get the iteration counts?
So I think I don't have them right now, but I can get them for you. I think ProxSDP does way more iterations than SCS, because I think their iterations are actually smaller, because SCS will do the primal-dual thing, so I think it doubles the size, so actually multiplies by 4 the size of the problem. And ProxSDP will keep like the SDP part of the problem will be kept in the primal form, so you only have a much smaller matrix. Maybe that's kind of the 2-factor, which is actually more, should be a 4-factor, but easier to explain something like that.
So how well do you think your solver can support sparse matrices?
So that's one of the future work questions. The problem is that, actually, one question: which matrix do you want to be sparse? The SDP matrix or the A matrix? The problem with the SDP matrix is the following: during the iterations of the algorithm, the SDP matrix moves slowly and moves a lot from the initial point to the end point of the system. So although you can start that sparse and end that sparse, the path it does to reach from one point to the other, it passes through many matrices that are not sparse. And this is one problem. But if you know in advance that your matrix is, for example, block diagonal, you could decompose those blocks, which is basically chordal decomposition. You could decompose those blocks, and then you solve for each of the blocks separately, and you have much smaller eigenvalue decompositions because they scale cubically. So that would be much easier. We try to think that the X matrix was sparse during the whole problem, or it has like really small rank by trying to use some sketch techniques from Joel Trupp. But it turns out that in between the initial point and the optimal point, there are some matrices that are pretty weird over there. So handling sparsity is hard because it changes a lot the pattern during the algorithm.
And it's not possible to just fix the sparsity pattern if you know it, and then use that somehow.
Probably. I haven't tried that. But yeah, if you have some strong prior on the sparsity pattern of your matrix,
Right, the pattern is fixed.
you probably can do something much better. So the achievements, we made a primal-dual method for solving SDPs. Actually, a first-order primal-dual method for solving SDPs. It exploits the low-rank structure of the problem. It's available online, so everybody can see it right now, although it doesn't have a paper or a very good README. And some future ideas is explore properties of the low-rank recovered solution, because that's something we've seen in the last results, is that solving this problem with ProxSDP typically leads to a very low-rank solution, while using CSDP, for instance, the solutions have much higher rank. Please?
Are there cases like looking for tools where you can
I'm sorry?
Are there cases, practical cases, in which you can guess the rank of your solution beforehand?
There are cases.
For workflow, we know that we can get some
Yes.
relaxation.
Yes.
This is the same for your function.
Yes. So this is something interesting. When solving optimal power flow problems, although you, in some instances, although you know the rank of that instances will be 1, if you fix 1 throughout the whole algorithm, that will not do good because it kind of needs to pass through a rank 3 solution to go back to a rank 1 solution. That's something interesting that we saw implementing the algorithm. But it stays low rank during the whole processes. Over? So the next step is combine the proposed method with Cordell techniques. So you can exploit block matrices. And so you do just spectral decomposition on the small blocks instead of having to do the spectral decomposition on the whole thing. And it's a proximal solver. So we have a step for doing the projection on the SDP cone, but there's nothing stopping us from, only time, from projecting also on other cones. So you could possibly add second order cones, exponential cones, and all those kind of cones would have like mostly nice proximal operators. And so this shouldn't be too hard also.
When you project to the SDP cone, you can also project to lower rank than what you would get.
The other cones, I would not know what happens for low rank. The SDP cone, we know how to handle low rank. But for instance, if you want to solve optimal power flow, you might want to model some of the constraints with second order cones instead of only SDPs. So you can reduce your SDP matrix. And then having those cones doing a fast projection might give some space for the SDP part to be solved faster.
But then it's not clear that you can enforce the low rank
Yes,
there.
exactly.
In the SDP, enforcing low rank is the same. So this truncation to project, you can also use it to truncate more and get
Exactly.
low rank solutions.
Yeah, I think that's it. Running out of time, or so I can show you a little bit more. Am I running out of time? Do I have I have 3 minutes. So I just made this notebook real quick just to show, well, in some sense I'm showing a little bit of MOI also, but I'm showing the solver working. So if you copy that and download the solver, that should work. Well, there are some versions of MOI that work and some that doesn't for now, but most of them do work. So I'm loading the ProxSDP and the MathOpt interface. Then I create a model with the MOIU, which is something that Miles or Benoit might talk a little bit later. And then I create this optimizer just using the ProxSDP optimizer and some structure to handle data. And then you can write, for instance, this is a simple LP. So you add 3 variables to be the triangle of a semidefinite matrix. And then you add this semidefinite constraint. This is just to represent positiveness of the variables. I will not use variable number 2. It's just a 2x2 optimization problem. Then I can add a constraint using a scalar function inside of a less than 4 set, and another constraint of a similar description. And then you can add an objective function, which is a find function with these terms, which is 4 times x1, 3 times x3. And then you say that I'm maximizing. And then you can optimize that with the MOI structures. And then there's a bunch of logging. And then you can query the results with MOI. And this is just one simple LP example. at the end there is the multiple input, multiple output example. So you just load all the data, create some random signal, you empty the optimizer, you create the variables, create the constraints, just like before, and then you add more constraints, add the objective function, solve the problem, query solutions. This is the whole solution thing, the whole solving process. And so, okay, S was the input signal, and then this last column of the matrix is where it lives the solution. So this last column, except for this last number 1 here, should match the input data. So this was just to show a little bit of MOI. Okay.
If you don't know what MOI is, I'm talking about it tomorrow.
Da-da-da-dun.
So let's thank Joaquim.
Thank you.
Actually, I have a question. What's
Yes.
Lacombe?
What?
What's Lacombe?
My bad.
Lacombe.
Ah, Lacombe. It's just a last name, a French last name.
But it's not your last name.
I have like 4 last names.
Also, Garcia. Okay, because I couldn't find your Twitter handle.
Oh,
So
my
it's-
bad.
Not everybody is on Twitter.
Oh,
But I knew because I saw his picture.
Yes.
I knew you were on Twitter, but couldn't find the handle.
yes. But that's me.
How did you find this picture on Twitter?
No, because he followed me and I saw his picture. I was like, who is Joaquim Lacombe? I saw his picture. Oh, it's Joaquim.
Yes.
But now, Tiago Serra was the one that had pointed out. I was like, Joaquim is Joaquim Lacombe.
Yeah. I used to make teachers crazy with that. Just use one last name at a time and they would be like, who are you?
Okay, well, one more question.
Have you looked at possibly extending these methods or STPs with binary variables and doing branching in combination with certain STPs in this way?
Actually, Mario wanted to use this to explore relaxations of binary problems, but we never wanted to solve a problem with binary variables in the problem, like only for the relaxations. And he dreams, of course, of doing branching bound with SDP instead of linear programming. That's his dream, but I think it's too slow for that.
Wish list for JuMP.
Yes.
A generic branching bound solver.
Yeah, exactly.
Yes.
Where's the
That's probably not too far for Jump.
Yes.
Yeah, let's thank him once again.
Thank you.